The traditional union find method algorithm might not seem very efficient. After all, the find operation could be O of n in the worst case. However, there are two straightforward optimizations that we can apply here that will bring amortized time close to O of 1 for both union and find operation. So first, we want to track in the size of each set. This helps us to ensure that the tree steps is minimized so that we can ensure that the smaller set is attached onto the larger set and not the other way around. And the modification here for this are in the union method. And then let's change the find method. We're keeping track of all of the nodes along the path so that afterwards we can make each of the nodes directly as the root, so that next time any of those nodes are searched for, it is only O of 1 time. So these modifications for this are all in the find method. Let's say we have a node and we assign them to the new variable root, and then we know the parent at root, right? And we assign them to the root variable, and then we have a new parent at root, right? So we do this again and again and again until the root is equal to parent at root. So this is a while loop. While the root is not equal to parent at root, we use this while loop to find the root, and then we know the A, we know the root, and we know the parent at A. And then we assign the parent at A to the old root, and then we assign the root to the parent at A, and then we assign old root to the A, and then we assign parent at A to the old root, and then we assign root to the parent at A, and then we assign old root to the A. So this is a while loop. While the A is not equal to root, it will compress the path, make the node A directly pointing to the root. So these two while loop traversal is form a method, which is iterative find at A. We just go to the find method and we create a new variable root to avoid confusion. We just want to know root here. So we just assign A into the root and change every A into the root. While root is not equal to parent at root, we update root variable assigned by the parent at root. So this will finally get the root. In the second step, we just create second traversal. While A is not equal to root, we create a new variable, old root, and assign parent at A into it. And then we assign root into parent at A and assign the old root into A. So this time we just set in the node pointing directly at A as we go. Let's say we have 6 nodes here, which is 0, 1, 2, 3, 4, 5, and then let's check the edge 0 and 2. We compare the size of 0, which is 1, which is equal to size of 2. So we assign 0 become the parent of 2, and then we update the size at 0 increment by the size of 2, which is now 1 plus 1 become 2. And then let's check the edge 4 and 1. We compare the size of 4, which is 1, which is equal to size of 1, and then we assign 4 become the parent of 1, and then we update the size of 4, increment by size of 1, which is 1 plus 1 become 2. And then we check the edge 2 and 3. Because 0 is 2's root node, so we compare the size of 3, which is 1, which is less than the size of 0, which is 2. So we assign 0 become the parent of 3, and then we update the size of 0 increment by the size of 3, which is 2 plus 1 is 3. And now let's check the edge 3 and 5. Because 0 is 3's root node, so we compare the size of 5, which is 1, which is less than the size of 0, which is 3. So we assign 0 become the parent of 5, and then we update the size of 0 increment by the size of 5, which is 3 plus 1, which is 4. And finally, let's check the edge 1 and 3. Because 0 is 3's root node and 4 is 1's root node, so we just compare the node 0 with node 4. The size of 4 is 2, which is less than the size of 0, which is 4. So we assign 0 become the parent of 4, and then we update the size of 0 increment by the size of 4, which is 4 plus 2 becomes 6. we go to the initialize constructor and we create a new set, size. So this array will keep track of the size of each set. And initially, every size is 1 and multiply by n because we have n set. Let's go back to the union method, and this time we want to change the logic of how merge happened. We want to ensure that the larger set remains the root. So we use the if statement. If the size of root A is less than the size of root B, this time we assign root B to the parent of root A, so it will make the root B the overall root. And then we increment the size of root B by the size of root A, so the size of the set rooted at B is the sum of the two sets. And else, when the size of root A is greater than or equal to the size of root B, we assign the root A to the parent of root B, so this will make the root A the overall root. And then we update the size of root A incremented by the size of root B, so this will make the size of the set rooted at A is the sum of the two sets. And about the optimization version of the union find approach, this keeps the tree steps very shallow. It turns out that the find method amortizes to O of alpha of n time, where the alpha is the inverse increment function. And this incredible thing about this function is that it grows so slowly that the n never go higher than 4 in the universe as we know it. So while in practice it was effectively O of 1 time, but in theory it is not.